In the vast darkness of space, there exist objects so strange, so powerful, that they challenge everything we thought we knew about the universe. These are black holes, and today, we're going to explore their mysteries together. The term black hole wasn't always what we called these cosmic enigmas. The name was actually coined by physicist John Wheeler in 1967, though the concept had been theorized much earlier. Before that, scientists referred to them by more cumbersome names like gravitationally completely collapsed objects. Imagine standing at the edge of understanding, where even light itself cannot escape. That's what a black hole is at its most fundamental level. A black hole is a region in space where gravity is so incredibly strong that nothing, not even light, can break free once it crosses a certain boundary. This boundary has a name that sounds almost poetic: the event horizon. The event horizon isn't a physical surface you could touch. It's more like an invisible threshold, a point of no return. Cross it, and you're committed to a journey toward the center, what we call the singularity. At the heart of every black hole lies the singularity, a point where matter is crushed to infinite density and the laws of physics as we understand them break down completely. It's a place where space and time become so warped that our current mathematical models simply stop working. But how do these remarkable objects come to exist? The story often begins with stars. The most common type of black hole, stellar black holes, are born from the death of massive stars. When a star at least 20 times more massive than our Sun exhausts its nuclear fuel, it can no longer support itself against its own gravity. The core collapses in a catastrophic implosion, creating a supernova explosion, and what remains can become a black hole. This process happens surprisingly often, in cosmic terms. Scientists estimate that there are roughly 100 million stellar black holes in our Milky Way galaxy alone. They're scattered throughout the galaxy, most of them solitary and invisible, detectable only by their gravitational effects on nearby objects. Some black holes, though, are far larger than these stellar remnants. Supermassive black holes contain millions to billions of times the mass of our Sun. These giants don't form from collapsing stars. Instead, they likely grew over billions of years, either from smaller black holes merging together or by continuously consuming surrounding matter. Nearly every large galaxy, including our own, harbors a supermassive black hole at its center. Our own galactic center holds one of these titans. The supermassive black hole at the center of the Milky Way is called Sagittarius A. It has a mass approximately 4 million times that of our Sun, yet despite its enormous mass, it sits relatively quiet, about 26,000 light-years away from Earth. As we observe black holes from our safe distance, we've discovered they do something quite unexpected. Black holes aren't completely black. In 1974, Stephen Hawking theorized that black holes emit radiation due to quantum effects near the event horizon. This Hawking radiation means black holes very slowly lose mass over time, eventually evaporating, though this process would take an almost incomprehensible length of time for stellar and supermassive black holes. And there's something else extraordinary about approaching a black hole. If you could somehow survive falling toward a black hole, time itself would behave strangely. Due to Einstein's theory of relativity, time moves slower in stronger gravitational fields. To a distant observer, you would appear to slow down as you approached the event horizon, never quite seeming to cross it, frozen in time at the threshold. But from your perspective, you would cross the horizon in a finite amount of your own time, unaware of anything special happening at that exact moment. These 9 facts are just the beginning of our journey into the heart of darkness, where the universe reveals its most extreme nature. As we venture deeper into understanding black holes, we discover that they're not just destroyers of matter and light. They're also sculptors of the cosmos itself. Black holes can actually create stars. The intense gravitational forces and energetic jets that some black holes produce can compress nearby gas clouds, triggering the birth of new stars. In this way, black holes become both endings and beginnings, participating in the eternal cycle of cosmic creation and destruction. The power that black holes wield extends far beyond their immediate surroundings. When matter falls into a black hole, it doesn't simply disappear quietly. As material spirals inward, it forms what's called an accretion disk, a swirling disk of gas and dust that heats up to millions of degrees through friction. These accretion disks are among the brightest objects in the universe, visible across billions of light-years, even though the black hole itself remains dark. Some black holes take this display of power even further. Certain black holes produce enormous jets of particles and energy that shoot out from near their poles at nearly the speed of light. These jets can extend for hundreds of thousands of light-years into space, dwarfing entire galaxies. The mechanism behind these jets involves the black hole's rotation and magnetic fields threading through the accretion disk, though scientists are still working to understand the complete picture. Speaking of rotation, black holes spin, and their spin tells us something profound. All black holes rotate, spinning at different speeds based on their history. Some spin relatively slowly, while others rotate at nearly the maximum possible rate, completing hundreds of rotations per second. A black hole's spin rate depends on how it formed and what it has consumed. When black holes merge, they can create a new black hole with a spin that combines aspects of both parents. The variety of black holes is more diverse than you might imagine. There are actually three main types of black holes, classified by their mass. Stellar black holes range from about 5 to 100 times the mass of the Sun. Supermassive black holes contain millions to billions of solar masses. And then there are intermediate mass black holes, ranging from 100 to 100,000 solar masses, which are rarer and more mysterious, possibly forming through different mechanisms entirely. But could there be something even smaller? Scientists have theorized about primordial black holes, tiny black holes that might have formed in the first moments after the Big Bang, when the universe was extremely dense. These would be much smaller than stellar black holes, potentially ranging from microscopic sizes to about the mass of Earth. While we haven't confirmed their existence yet, if they do exist, they could account for some of the mysterious dark matter in the universe. The search for black holes has led to one of humanity's greatest technological achievements. In 2019, scientists revealed the first ever direct image of a black hole shadow. The Event Horizon Telescope, a network of radio telescopes spanning the entire Earth working together as one giant telescope, captured an image of the supermassive black hole at the center of the galaxy M87. The image showed a bright ring of light surrounding a dark center, exactly matching predictions from Einstein's equations written over a century ago. And just 3 years later, we captured another portrait. In 2022, the Event Horizon Telescope released the first image of Sagittarius A*, our own galaxy's supermassive black hole. This image was actually more difficult to capture than M87's black hole, even though Sagittarius A* is much closer to us. The material around Sagittarius A* orbits much faster, changing in mere minutes, making it like trying to photograph a restless child compared to M87's more steady, adult demeanor. With each discovery, black holes shift from abstract mathematics to tangible reality, objects we can observe and study, even as they remain among the most mysterious phenomena in existence. The story of black holes is also the story of how we came to understand them, a journey that required reimagining the very fabric of reality. The first mathematical description of what we now call a black hole came surprisingly early, in 1916, just months after Einstein published his theory of general relativity. German physicist Karl Schwarzschild, while serving in World War I, derived a solution to Einstein's equations that described a point mass with such extreme gravity that nothing could escape it. Einstein himself was skeptical that such objects could actually exist in nature. The universe, as it turns out, had no such reservations. The first strong candidate for a real black hole was discovered in 1964. An X-ray source called Cygnus X1, located about 6,000 light-years from Earth, appeared to be a black hole feeding on a companion star. The evidence was so compelling that Stephen Hawking famously made a bet in 1974 that it wasn't a black hole, a bet he later conceded in 1990 when the evidence became overwhelming. Black holes reveal themselves through their relationships with other objects. When a black hole has a companion star, it can pull material away from that star in a process called stellar cannibalism. The stolen gas doesn't fall directly in, but instead spirals around the black hole, heating up and emitting powerful X-rays that we can detect from Earth. This is one of the primary ways we identify black holes, by watching them feed. But feeding on a companion star isn't the only meal a black hole can have. Sometimes, an entire star wanders too close to a black hole and gets torn apart by tidal forces in an event called, rather dramatically, a tidal disruption event. The star is stretched and shredded like cosmic spaghetti, with about half of its material falling into the black hole while the rest is flung back into space. These events can cause a black hole to suddenly brighten by factors of thousands, creating a brilliant flare visible across the universe. This stretching effect has an equally dramatic name. The term spaghettification is the actual scientific term for what would happen to you if you fell into a black hole. The gravitational force on your feet would be so much stronger than on your head that you'd be stretched into a long, thin strand. For smaller black holes, this would happen before you even reached the event horizon. Interestingly, with supermassive black holes, their event horizons are so large that you could actually cross it before being spaghettified, experiencing relatively gentle conditions at first. The influence of black holes extends across cosmic distances in ways both subtle and dramatic. Black holes can act as gravitational lenses, bending the light from objects behind them due to their intense gravity warping space-time. This effect, predicted by Einstein, allows us to see distorted, magnified, or even multiple images of distant galaxies. Some black holes create perfect circles of light called Einstein rings when the alignment is just right. In recent years, we've discovered an entirely new way to detect black holes. On September 14, 2015, humanity directly detected gravitational waves for the first time. These ripples in space-time were created by two black holes, each about 30 times the mass of the Sun, spiraling into each other and merging 1.3 billion light-years away. The collision released more energy in a fraction of a second than all the stars in the observable universe combined, though it released this energy as gravitational waves rather than light. This detection opened a new window into the universe. The LIGO and Virgo gravitational wave observatories have now detected dozens of black hole mergers. Each collision tells us something new, revealing a population of black holes we never knew existed. Some of these mergers involve black holes more massive than scientists thought possible from stellar collapse, suggesting they might be second-generation black holes formed from previous mergers. Black holes also help us understand the structure of the universe itself. Supermassive black holes appear to play a crucial role in galaxy evolution. There's a mysterious relationship between the mass of a galaxy's central supermassive black hole and the properties of the galaxy itself. Somehow, even though the black hole is tiny compared to the galaxy, the two grow together in lockstep, suggesting a deep connection we're still working to understand. And the engines they power are among the most energetic in the cosmos. When supermassive black holes actively feed on surrounding matter, they can power quasars, the brightest sustained objects in the universe. A single quasar can outshine an entire galaxy of hundreds of billions of stars, visible from across the observable universe. These cosmic lighthouses were especially common in the early universe, suggesting that galaxy formation and black hole growth were intimately connected in the cosmos's youth. From mathematical curiosities to cosmic architects, black holes continue to surprise us, their influence woven into the very structure of the universe. As we continue our exploration, we find that black holes challenge not just our understanding of space, but of time itself, and even the fundamental nature of information. Inside a black hole, space and time actually switch roles. Outside the event horizon, you can move freely through space but are forced forward in time. Inside the event horizon, you can move freely through time's direction, but you're forced inward through space toward the singularity. It's not just that you can't escape, the singularity is literally in your future, not in a direction you could turn away from. This strange nature leads to one of physics' greatest puzzles. The black hole information paradox has puzzled physicists for decades. When something falls into a black hole, quantum mechanics says the information about its quantum state should be preserved somehow. But Hawking radiation appears to be random, carrying no information about what fell in. This creates a paradox. Does the information disappear, violating quantum mechanics, or is it preserved somehow? The question remains one of the deepest mysteries in theoretical physics. Black holes exist in sizes that span an almost incomprehensible range. The smallest black holes that could form from stellar collapse are about 5 solar masses, which would have an event horizon roughly 30 kilometers across, smaller than most cities. Meanwhile, the largest known supermassive black holes contain tens of billions of solar masses, with event horizons that could encompass our entire solar system several times over. That's a size range of billions to 1. Some black holes stand out as truly exceptional. The black hole at the center of the galaxy TON 618 is one of the most massive ever discovered, weighing in at approximately 66 billion solar masses. Its event horizon would have a diameter of about 1,300 astronomical units. That's 1,300 times the distance from Earth to the Sun. If it replaced our Sun, its event horizon would extend far beyond Neptune's orbit. Black holes can create conditions found nowhere else in the universe. Near the event horizon of a rotating black hole, there exists a region called the ergosphere where space-time itself is dragged around by the black hole's rotation. In this region, it's impossible to stand still. You're forced to move in the direction of the black hole's spin. Theoretically, it's possible to extract energy from a rotating black hole by entering the ergosphere, a process called the Penrose process. The behavior of matter near black holes reaches extremes we can barely imagine. Material in an accretion disk around a black hole can orbit at significant fractions of the speed of light. For stellar mass black holes, matter can complete an orbit in mere milliseconds. At these speeds, relativistic effects become extreme. Time slows down dramatically, lengths contract, and the mass of particles effectively increases due to their tremendous kinetic energy. Black holes might not be the final state of matter after all. Some theoretical physicists propose that black holes might eventually transform into white holes, hypothetical regions of spacetime that are the opposite of black holes. Nothing can enter them, but matter and light can escape. While white holes are mathematically possible solutions to Einstein's equations, we have no evidence they actually exist, and most physicists consider them unlikely to occur in nature. The connection between black holes and the quantum world runs deep. Black holes have entropy, a measure of disorder, proportional to the surface area of their event horizon rather than their volume. This discovery, formalized in the Bekenstein-Hawking formula, suggests that all the information about what's inside a black hole might somehow be encoded on its two-dimensional surface. This idea has led to the holographic principle, which proposes that our entire three-dimensional universe might be encoded on a two-dimensional boundary, like a hologram. Black holes can form through unexpected means. In the early universe, areas with slightly higher density than their surroundings might have collapsed directly into black holes without ever forming stars first. These primordial black holes, if they exist, could have formed within the first second after the Big Bang. Some could be microscopic, even subatomic, while others might be planet-sized or larger. Their existence remains speculative, but they're an active area of research. And in our search for dark matter, black holes remain candidates. Dark matter makes up about 85% of all matter in the universe, yet we don't know what it is. Some scientists have proposed that primordial black holes could account for at least some of this dark matter. However, various observations and experiments have ruled out primordial black holes as the dominant source of dark matter, though they could still contribute a small fraction. The mystery of dark matter remains largely unsolved. Through paradoxes and possibilities, black holes continue to push the boundaries of what we think is possible, inviting us to question the very nature of reality. As we venture further into the realm of black holes, we discover that they're not isolated objects, but participants in a cosmic dance that shapes the destiny of galaxies and perhaps even universes. Black holes can merge not just in pairs, but potentially in complex multiple systems. When galaxies collide and merge, their central supermassive black holes eventually spiral toward each other, creating a binary black hole system. In dense stellar environments, these binaries might even encounter third black holes, leading to chaotic gravitational interactions that can fling black holes out of galaxies at speeds of thousands of kilometers per second. Some black holes wander through space completely alone. Rogue black holes, ejected from their home galaxies through gravitational interactions or asymmetric gravitational wave emission during mergers, drift through intergalactic space. These solitary travelers are extremely difficult to detect because they have nothing nearby to feed on and thus produce no light. Scientists estimate there could be millions of these wandering black holes throughout the universe, invisible nomads in the cosmic dark. The environment immediately around a black hole is one of the universe's most extreme laboratories. The magnetic fields near black holes can be extraordinarily powerful, potentially reaching strengths of billions of Tesla, trillions of times stronger than Earth's magnetic field. These fields play a crucial role in launching the relativistic jets we see from some black holes, channeling and accelerating particles to nearly light speed through processes we're still working to fully understand. Time behaves so strangely near black holes that it creates paradoxes. If you watched a clock fall into a black hole while you remained at a safe distance, you would see the clock slow down as it approached the event horizon, its ticks becoming longer and longer, the light from it becoming redder and dimmer. Theoretically, you would never actually see it cross the horizon. It would appear frozen there forever, fading from view. Yet from the clock's perspective, it would cross the horizon in finite time and reach the singularity shortly after. Black holes might be connected to the very birth of the universe. Some cosmologists have proposed that our entire universe might exist inside a black hole, or that black holes in our universe might contain entire universes within them. While highly speculative, these ideas emerge from attempts to understand what happens at the singularity and to connect quantum mechanics with gravity. Each black hole might birth a new universe, leading to a multiverse of bubble universes, though this remains firmly in the realm of theoretical speculation. The deaths of black holes, should they occur, would be spectacular. As a black hole evaporates through Hawking radiation, it actually gets hotter and radiates faster, accelerating its own demise. In its final moments, a black hole would explode in a brilliant flash of energy. However, for a stellar mass black hole, this process would take approximately 10 to the power of 67 years, incomparably longer than the current age of the universe, which is only about 14 billion years. Not all black holes spin around a single axis. Black holes can wobble or precess, much like a spinning top. When a black hole's spin axis is tilted relative to the plane of its accretion disk, the disk itself can warp and precess. This effect, called lens-thirring precession, is a consequence of general relativity and has been observed in several black hole systems, causing periodic variations in the X-ray emissions we detect. The nearest black hole to Earth has been a subject of changing discovery. For years, the nearest known black hole was thought to be about 1,000 light-years away. However, in 2022, astronomers discovered a dormant black hole in a binary system just 1,600 light-years from Earth in the constellation Ophiuchus. Then in 2023, data suggested an even closer one, Gaia BH1, at approximately 1,560 light-years away. These sleeping black holes, not actively feeding, are harder to find but likely far more common than their active cousins. Black holes can create their own weather systems. The accretion disks around some black holes display phenomena similar to weather patterns on Earth. Scientists have observed what they call winds and storms in these disks, outflows of material driven by radiation pressure and magnetic fields. Some black holes experience quasi-periodic oscillations, rhythmic variations in brightness that might be caused by structures orbiting in the inner accretion disk, like cosmic storms circling the drain. And they can even influence the chemistry of the universe. The extreme environments near black holes can forge heavy elements through nuclear processes. The intense heat and pressure in material orbiting black holes, as well as in the debris from neutron star mergers that often create black holes, can produce rare heavy elements like gold, platinum, and uranium. In this way, black holes participate not just in destroying matter, but in enriching the universe with the building blocks of planets and life. From wanderers in the void to forgers of creation, black holes reveal themselves as far more than cosmic vacuum cleaners. They're integral players in the universe's grand story. As we reach the midpoint of our journey through black hole mysteries, we find ourselves confronting some of the strangest predictions and most profound questions in all of science. The concept of a photon sphere exists just outside a black hole's event horizon. This is a region where gravity is so strong that light can orbit the black hole in circular paths. If you could somehow position yourself in the photon sphere and look in just the right direction, you could theoretically see the back of your own head, as light from you would circle around the black hole and return to your eyes. Some black holes defy our expectations in remarkable ways. Intermediate mass black holes, ranging from 100 to 100,000 solar masses, are surprisingly elusive. While we found many stellar black holes and supermassive black holes, intermediate mass black holes have been harder to confirm. Scientists suspect they might form in dense star clusters where stars repeatedly collide and merge, or they might be the seeds from which supermassive black holes grow, but their relative rarity remains puzzling. The mathematics of black holes leads to concepts that sound like science fiction. Rotating black holes, described by the Kerr solution to Einstein's equations, theoretically contain not one but two event horizons. Between these horizons lies the ergosphere we mentioned earlier. Even more fantastically, the mathematics suggests that the singularity inside a rotating black hole isn't a point but a ring, and passing through this ring might, at least mathematically, lead to other universes or other regions of spacetime, though most physicists believe quantum effects would prevent this in reality. Black holes remember surprisingly little about what falls into them. According to the no-hair theorem, a black hole can be completely described by just three properties: its mass, its electric charge, and its angular momentum or spin. Everything else about what fell in, whether it was stars, planets, antimatter, or pizza, is lost. This simplicity is both elegant and troubling, as it seems to violate the principle that information cannot be destroyed, leading back to the information paradox we discussed earlier. The power output from black holes can be staggering. Some black holes, particularly those in active galactic nuclei, can convert matter to energy with stunning efficiency. While nuclear fusion in stars converts less than 1% of mass into energy, a black hole's accretion process can convert up to 40% of infalling matter into radiation and kinetic energy in jets. This makes actively feeding black holes the most efficient engines of energy production in the known universe. Black holes can create unusual partnerships with other extreme objects. When a black hole orbits a neutron star, another extremely dense stellar remnant, the pair creates a binary system that's a goldmine for physics. As they spiral together, the black hole can tidally disrupt the neutron star, tearing it apart before swallowing it. The gravitational waves from such mergers, first detected in 2019, carry unique signatures that tell us about the properties of both objects and even about the behavior of matter at nuclear densities. The visualization of black holes involves fascinating optical illusions. When we see images or simulations of black holes, we're actually seeing a shadow that's larger than the event horizon itself. This is because light that passes close to the black hole gets bent around it, creating a dark region about 2.6 times larger than the actual event horizon. This shadow is surrounded by a bright ring of light from the accretion disk, including light from the backside of the disk that's been bent over and around the black hole to reach our eyes. Black holes could theoretically be used as incredible energy sources. In 1969, physicist Roger Penrose proposed that an advanced civilization could extract energy from a rotating black hole by dropping material into the ergosphere. The Penrose process could theoretically extract up to 29% of a black hole's rotational energy. Later, physicists showed that the same principle could work with magnetic fields threading through the black hole, a process that might already be powering the jets we observe from active black holes naturally. The universe's first black holes formed in an era we're only beginning to understand. Astronomers have discovered quasars powered by supermassive black holes that existed when the universe was less than 1 billion years old, just 7% of its current age. These early black holes, containing hundreds of millions or even billions of solar masses, grew to enormous sizes remarkably quickly. How they formed and grew so fast remains one of astronomy's great puzzles, challenging our theories of black hole formation and growth. and black holes might solve a mystery about the universe's future. In the far distant future, in what cosmologists call the black hole era, black holes might be the only significant structures remaining in the universe. After all stars have died and even white dwarfs and neutron stars have decayed, black holes will persist, slowly evaporating through Hawking radiation. This era would last from about 10 to the power of 40 years until perhaps 10 to the power of 100 years after the Big Bang, an almost incomprehensible span of time during which the universe would be a cold, dark place punctuated only by the faint glow of evaporating black holes. Halfway through our exploration, we find that each answer about black holes raises new questions, each solution reveals deeper mysteries, drawing us further into the beautiful complexity of the cosmos. As we continue deeper into the nature of black holes, we find that these objects connect to nearly every aspect of modern physics, from the quantum to the cosmic. Black holes can actually evaporate completely, at least in theory. Through Hawking radiation, they slowly lose mass over time. Smaller black holes evaporate faster than larger ones. A black hole with the mass of a car would evaporate in a tiny fraction of a second, while one with Earth's mass would take about 10 to the power of 50 years. The smallest black holes would end their lives in spectacular explosions, releasing as much energy as millions of nuclear bombs. The way we detect black holes has become remarkably sophisticated. Modern astronomers use multiple methods to find black holes. They track stars orbiting invisible companions, measuring the wobbles in the star's motion. They detect X-rays from superheated material spiraling into black holes. They observe gravitational waves from merging black holes. They even watch stars being torn apart in tidal disruption events. Each method reveals different populations of black holes, painting a more complete picture of their abundance and diversity. Black holes challenge our understanding of what inside even means. From the perspective of someone falling into a black hole, they would cross the event horizon and continue inward, experiencing increasingly extreme tidal forces. But from the outside perspective, due to time dilation, you would never see them actually cross. This creates a strange duality. Both perspectives are equally valid in their own reference frames, yet they describe completely different realities. This is one of the profound lessons of relativity. Reality depends on perspective. Some black holes are extraordinarily hyperactive. Blazars are a special type of active galactic nucleus where supermassive black holes jet points nearly directly at Earth. Because we're looking straight down the barrel of the jet, so to speak, these objects appear incredibly bright and can vary dramatically in brightness over just days or even hours. They're among the most violent and energetic phenomena in the universe, with some blazars emitting gamma rays with energies millions of times greater than visible light. Black holes exist in our cosmic neighborhood more than we once thought. Recent studies suggest there may be tens of millions of stellar mass black holes in our Milky Way galaxy alone, far more than earlier estimates. Most of these are solitary and dormant, making them extremely difficult to detect. They're the remnants of massive stars that died throughout our galaxy's history, invisible ghosts scattered among the stars, detectable only when something passes close enough for their gravity to betray their presence. The geometry near a black hole creates mind-bending visual effects. If you could orbit close to a black hole and look at the star field around you, you would see the stars distorted into strange patterns. Stars behind the black hole would appear to wrap around it. You might see multiple images of the same star in different directions. The constellation patterns would be unrecognizable, warped by the intense gravitational lensing. Light from directly behind you might be bent around the black hole to appear in front of you. Black holes may have played a crucial role in cosmic history. In the early universe, the energetic jets and radiation from supermassive black holes may have helped end the cosmic dark ages by reionizing hydrogen gas throughout space. This epoch of reionization, which occurred a few 100 million years after the Big Bang, made the universe transparent to light and helped shape the large-scale structure of galaxies we see today. Black holes weren't just destructive forces, they were cosmic torches illuminating the infant universe. The extremes of physics meet at black hole surfaces. At the event horizon of a black hole, quantum mechanics and general relativity come into direct conflict. General relativity says nothing special happens at the horizon, you cross it smoothly. But quantum mechanics, through Hawking radiation, suggests the horizon is a place where particles are created and destroyed. This tension has led to radical proposals like the firewall paradox, which suggests the horizon might actually be a lethal wall of high-energy particles, contradicting general relativity's predictions. Black holes can form from more than just stars. In addition to stellar collapse and primordial formation, some theories suggest black holes could form through other exotic mechanisms. Direct collapse of massive gas clouds in the early universe might create black holes without forming stars first. Dark matter could potentially clump together densely enough to collapse into black holes. Some have even speculated about artificial black holes being created in the distant future by advanced civilizations, though creating one would require technology far beyond anything we can currently imagine. The spin of a black hole tells the story of its life. A black hole's rotation rate preserves information about its history. Black holes formed from stellar collapse typically rotate rapidly. Those that grow primarily by accreting gas tend to spin faster, while those that grow by randomly capturing stars or merging with other black holes at various angles tend to spin more slowly. By measuring a black hole's spin, astronomers can make inferences about how it formed and grew over cosmic time. And they connect to one of physics' holy grails. Black holes represent one of the key testing grounds for a theory of quantum gravity, the long-sought unification of quantum mechanics and general relativity. The singularity at a black hole center is a place where our current theories break down completely. Any successful theory of quantum gravity must be able to describe what happens there, resolve the information paradox, and explain the nature of Hawking radiation. Understanding black holes fully may require a revolution in physics as profound as relativity or quantum mechanics themselves. With each fact, we see how black holes weave through the tapestry of physics, connecting the smallest scales of quantum foam to the largest structures in the cosmos. As we near the end of our journey, we discover that black holes continue to surprise us, revealing connections to the very fabric of existence and our place within it. The boundary of a black hole, the event horizon, has no physical substance whatsoever. It's not a membrane or a surface you could touch, it's simply a mathematical boundary in spacetime, a point of no return defined purely by geometry. An astronaut crossing the horizon of a supermassive black hole might not even realize they've crossed it, at least not immediately, as there's no wall or barrier to mark the moment. Black holes can generate some of the fastest winds in the universe. The radiation pressure from material spiraling into a black hole can drive powerful winds that blow outward at speeds of up to 20% the speed of light. That's about 60,000 kilometers per second. These ultra-fast outflows carry enormous amounts of energy and can actually regulate how quickly a black hole feeds, creating a self-limiting mechanism. When the winds become too strong, they can blow away the very material that would otherwise fall into the black hole. Our understanding of black holes has been refined by Nobel Prize-winning work. In 2020, the Nobel Prize in Physics was awarded partly for black hole research. Roger Penrose won for proving mathematically that black holes are a direct consequence of Einstein's general relativity, showing that singularities must form under realistic conditions. Andrea Ghez and Reinhard Genzel won for discovering the supermassive compact object at our galaxy's center, providing the most convincing evidence that supermassive black holes truly exist. Black holes might be the ultimate cosmic recyclers. While we often think of black holes as cosmic vacuum cleaners that only consume, they also return energy to their environments. Through their jets, winds, and radiation from their accretion disks, black holes inject enormous amounts of energy back into surrounding gas. This feedback can heat gas, preventing it from cooling and forming new stars, effectively controlling the rate of star formation in galaxies. Without this regulation, galaxies might look very different than they do. The sounds of black holes merging have been translated for human ears. While gravitational waves aren't sound waves, they're ripples in space-time itself, scientists have converted the gravitational wave signals from merging black holes into audio frequencies humans can hear. These sounds start as a low-frequency chirp that rises in pitch and volume as the black holes spiral closer, ending in a final ringdown as the merged black hole settles into its final form. It's been described as a cosmic chirp or whoop that lasts just a fraction of a second. Black holes challenge the very concept of time. At the singularity of a black hole, where density becomes infinite, time as we understand it may cease to exist or become meaningless. Some physicists suggest that inside a black hole, the nature of time might be fundamentally different from anything we experience. The singularity represents not just a place where our equations break down, but potentially where the concept of when itself loses meaning. Not all encounters with black holes are fatal. It's theoretically possible to orbit a black hole safely, as long as you stay outside the innermost stable circular orbit. For a non-rotating black hole, this orbit exists at 3 times the radius of the event horizon. Closer than this, orbits become unstable and you'd spiral inward. But at or beyond this distance, you could orbit indefinitely, though you'd experience extreme time dilation, powerful tidal forces, and would be bathed in intense radiation from the accretion disk if one is present. Black holes may hold clues to the nature of dark energy. Some cosmologists have explored the possibility that black holes might be connected to dark energy, the mysterious force causing the universe's expansion to accelerate. One speculative idea suggests that the interiors of black holes might contribute to dark energy's repulsive effect. While this remains highly theoretical and contentious, it represents scientists' attempts to connect the physics of the very small, black holes and quantum mechanics, with the very large, the universe's expansion. The jets from black holes can affect entire galaxy clusters. The relativistic jets from supermassive black holes can carve enormous cavities in the hot gas surrounding galaxy clusters, creating bubbles that can span hundreds of thousands of light-years. These bubbles, visible in X-ray observations, represent a tremendous amount of energy, equivalent to billions of supernovae, being deposited into intergalactic space. This process affects how gas cools and flows in galaxy clusters, influencing the evolution of some of the largest structures in the universe. Black holes provide natural laboratories for testing Einstein's theories. The extreme gravity near black holes allows scientists to test general relativity in conditions impossible to recreate on Earth. Observations of stars orbiting Sagittarius A have confirmed predictions like the gravitational redshift of light and the precession of orbits, exactly as Einstein's equations predicted. Each observation that matches theory's predictions strengthens our confidence that we understand gravity correctly, even in these extreme environments. And finally, black holes remind us of the limits and reach of human understanding. Despite all we've learned about black holes over the past century, from mathematical curiosities to observed realities, from stellar remnants to galaxy-shaping giants, they remain in many ways mysterious. We still don't know what happens at the singularity. We haven't resolved the information paradox. We don't fully understand how the first supermassive black holes formed. These gaps in our knowledge aren't failures, they're invitations, pointing toward the discoveries that await future generations of scientists, explorers of the cosmos who will continue humanity's quest to understand the universe's most enigmatic objects. As we approach the final chapter of our journey, we find that black holes have taught us as much about the questions to ask as they have about the answers we seek. In these penultimate moments of our exploration, we discover the ways black holes connect to our own existence, to the technology we've built to study them, and to the future of cosmic exploration. The study of black holes has led to practical technological advances here on Earth. The algorithms developed to process the Event Horizon Telescope's data, combining observations from telescopes across the planet, have applications in medical imaging and other fields requiring the reconstruction of images from limited data. The computational techniques for simulating black hole physics have advanced our capabilities in handling complex systems across many scientific disciplines. Black holes can act as natural particle accelerators. The environments near black holes can accelerate particles to energies that rival or exceed the most powerful particle accelerators humans have built. Cosmic rays, high-energy particles that constantly bombard Earth, may originate from regions near black holes, particularly from the shock waves in their jets. Some of these particles carry energies millions of times greater than anything produced at facilities like the Large Hadron Collider. The mass of a black hole determines the fate of everything near it. There's a curious relationship between a black hole's mass and the experience of crossing its event horizon. For a stellar mass black hole of just a few solar masses, the tidal forces at the event horizon would be fatal. You'd be spaghettified before crossing. But for a supermassive black hole of 1 billion solar masses, the tidal forces at the horizon are actually quite gentle. You could cross it intact and survive for some time before the forces near the singularity become lethal. Black holes may be more common in binary systems than we realized. Recent observations suggest that many black holes exist in binary systems with ordinary stars, but remain undetected because they're not actively feeding. These dormant or quiescent black holes don't produce the X-rays that usually betray their presence. Astronomers are developing new techniques to find them by looking for the subtle gravitational influence they have on their companion stars, revealing a hidden population we're only beginning to count. The gravitational memory effect preserves evidence of black hole mergers. When two black holes merge, they create gravitational waves that permanently alter the fabric of spacetime even after the waves pass. This gravitational memory effect means that the merger leaves a lasting change in the distances between objects, though the effect is incredibly tiny. Detecting this memory effect could provide new information about black hole mergers and test our understanding of gravity in new ways. Black holes can help us peer into the earliest moments of cosmic history. By studying the most distant quasars, powered by supermassive black holes in the early universe, astronomers can learn about conditions when the cosmos was young. The light from these quasars has traveled for over 13 billion years to reach us, passing through clouds of gas along the way. By analyzing how this light is absorbed, scientists can map the evolution of the universe's chemical composition and structure across cosmic time. The innermost stable orbit around a black hole is a point of no return for matter. The innermost stable circular orbit, or ISCO, marks the closest distance at which matter can orbit a black hole before inevitably spiraling inward. For a non-rotating black hole, this is at 3 times the Schwarzschild radius. For maximally rotating black holes, it's much closer, just 1.5 times the radius of the event horizon. Material at the ISCO orbits at significant fractions of light speed, emitting intense radiation in its final moments before plunging in. Black holes challenge our intuitions about temperature. Counterintuitively, black holes have temperature, despite being black. Hawking radiation gives them a thermal temperature inversely proportional to their mass. The larger the black hole, the colder it is. A stellar mass black hole has a temperature of about 1/1000th of a degree above absolute zero, far colder than the cosmic microwave background. Only microscopic black holes would be hot enough to glow with significant radiation. The formation of supermassive black holes remains one of astronomy's greatest puzzles. Astronomers have found supermassive black holes containing billions of solar masses that existed when the universe was less than 1 billion years old. Growing to such enormous sizes so quickly is difficult to explain. Black holes grow by consuming matter, but there are physical limits to how fast they can feed. The radiation pressure from infalling material pushes away additional matter. This Eddington limit suggests these early black holes either formed unusually massive to begin with, or found ways to exceed the expected feeding rate. Black holes might be connected through wormholes in theoretical physics. The ER equals EPR conjecture, proposed by physicists including Juan Maldacena and Leonard Susskind, suggests a deep connection between quantum entanglement and wormholes. The idea proposes that 2 quantum-entangled black holes might be connected by a wormhole, a shortcut through space-time. While these wormholes would be non-traversable, the conjecture represents an attempt to unite quantum mechanics and general relativity, suggesting they might be 2 descriptions of the same underlying reality. And black holes offer a glimpse into the ultimate fate of matter itself. In the unimaginably distant future, if protons themselves eventually decay as some theories suggest, black holes might be the last organized structures containing significant mass. Even after all ordinary matter has decomposed, black holes would persist, evaporating slowly through Hawking radiation over timescales that make the current age of the universe seem like an eye blink. They represent not just the end states of massive stars, but potentially the final chapter in the story of matter itself. As we approach the culmination of our journey, these final facts remind us that black holes are not merely objects to study, but windows through which we glimpse the deepest truths about existence. And now, we arrive at the final chapter of our journey through the cosmos's most enigmatic phenomena. These last 10 facts bring us full circle, connecting black holes to the broadest questions of existence and our continuing quest to understand the universe. Black holes can collide not just with other black holes, but with neutron stars, creating hybrid merger events. These collisions are particularly valuable to scientists because neutron stars are made of normal matter, unlike black holes which are pure curved space-time. When a black hole tears apart a neutron star, the merger produces both gravitational waves and light, allowing us to study the event with multiple types of telescopes and learn about the composition of neutron stars. The search for black holes has revealed the diversity of stellar death. There appears to be a mass gap in observed black holes. Very few black holes have been found with masses between about 2 and 5 solar masses. This gap may represent a real divide in how massive stars die. Stars that produce remnants in this range might explode so energetically that they leave nothing behind, or the gap might reveal something fundamental about the physics of supernovae and neutron star formation that we don't yet fully understand. Black holes demonstrate the principle that nature has no obligation to make sense to us. The mathematics of black holes predicts phenomena that seem impossible: time stopping, space becoming inescapable, infinities in finite locations. Yet observation after observation confirms these predictions. Black holes teach us that the universe operates on principles that can be profoundly counterintuitive, that our everyday experience is a poor guide to cosmic reality, and that nature's truth is often stranger than any fiction we could imagine. The information paradox may point toward a revolution in physics. Various proposals to resolve the black hole information paradox suggest radical new physics. Some physicists propose that information is encoded in subtle correlations in Hawking radiation. Others suggest it's stored on the event horizon like a hologram. Still others propose that black holes don't fully evaporate but leave behind remnants containing the information. Each solution would require us to rethink fundamental aspects of physics, from locality to the nature of space-time itself. Black holes exist at the intersection of the largest and smallest scales in physics. The study of black holes requires understanding both general relativity, which governs gravity and the cosmos at large, and quantum mechanics, which governs the subatomic world. These two theories are incompatible as currently formulated, yet both are necessary to fully describe black holes. This makes black holes the perfect testing ground for theories of quantum gravity, where physicists hope to finally unite these two pillars of modern physics. The most extreme black holes spin at astonishing rates. The fastest spinning black holes rotate at nearly the maximum rate allowed by physics, approaching 1 rotation per millisecond for stellar mass black holes, or hundreds of rotations per second. At these speeds, they drag space-time around with them so dramatically that the very notion of stationary loses meaning near them. Nothing can remain still relative to distant space, everything must rotate with the black hole's spin. Black holes may preserve more information than the no-hair theorem suggests. Recent theoretical work suggests that black hole horizons might be more complex than previously thought. Quantum effects might give black holes soft hair, subtle quantum states on the horizon that could store information about what fell in. This challenges the classical no-hair theorem and offers a potential pathway toward resolving the information paradox, suggesting that black holes might remember more than just mass, charge, and spin. The cosmic web of the universe is shaped by black holes. Supermassive black holes don't just influence their host galaxies, their effects extend to the large-scale structure of the universe itself. The energy they inject into their surroundings affects how gas flows along the cosmic web, the vast network of dark matter filaments connecting galaxy clusters. In this way, black holes that are microscopic compared to cosmic scales help determine the distribution of matter across hundreds of millions of light-years. Observing black holes pushes our technology to its absolute limits. Creating the first image of a black hole required combining data from radio telescopes across the entire Earth, effectively creating a telescope the size of our planet. The data rate was so enormous that hard drives had to be physically shipped to a central location. It was faster than internet transfer. The computational power needed to process the data and create the image represented years of work by hundreds of scientists and engineers, a testament to human ingenuity and collaboration. And finally, black holes remind us of our place in the cosmos. Every atom in your body heavier than hydrogen and helium was forged in the heart of a star or created in the violent death of massive stars, events intimately connected to black hole formation. The carbon in your cells, the calcium in your bones, the iron in your blood, all were created through stellar processes. In studying black holes, we study the life cycle of stars, and in studying stars, we study our own origins. We are, quite literally, made of stardust, and black holes are part of the cosmic story that made us possible. And so we reach the end of our journey through 100 facts about black holes. From mathematical abstractions to observed realities, from stellar remnants to galaxy-shaping giants, from the event horizon's point of no return to the unknowable singularity within, black holes have revealed themselves as far more than cosmic curiosities. They are the universe at its most extreme, places where the laws of physics are pushed to their breaking points and beyond. They are laboratories where space and time intertwine, where matter and energy dance at the edge of annihilation, where the quantum world meets cosmic-scale gravity. But perhaps most profoundly, black holes are mirrors reflecting our own quest for understanding. Each mystery we've unraveled has revealed deeper mysteries. Each question we've answered has spawned new questions. The information paradox, the nature of singularities, the connection between black holes and quantum mechanics, these puzzles await future generations to solve. As you drift off to sleep tonight, know that somewhere in the cosmos, black holes are being born in stellar deaths. Others are merging in collisions that shake the fabric of space-time itself. Material is spiraling into accretion disks, heating to millions of degrees, shining across billions of light-years. Jets are launching at near light speed, carrying energy across intergalactic distances. And at the center of our own galaxy, Sagittarius A* sits quietly, a 4 million solar mass giant waiting patiently, as it has for billions of years. These cosmic enigmas, invisible yet undeniable, destructive yet creative, simple in description yet infinite in mystery, continue their eternal dance through the darkness of space. And we, tiny beings on a small planet orbiting an ordinary star, have reached out with mathematics and observation, with ingenuity and wonder, to touch the untouchable and know the unknowable. The universe may not owe us clarity, but it has given us black holes, teachers of humility, inspirations for wonder, and invitations to keep exploring, keep questioning, keep reaching toward understanding. May your dreams be filled with the mysteries of the cosmos, and may you wake with a renewed sense of wonder at the strange and beautiful universe we call home.